Hello and welcome to a series of short talks about equivalent networks. As well as defining what an equivalent network is, we'll be covering the following topics. A quick revision of the principle of superposition and the idea of linearity in networks, because a lot of what we'll be doing on equivalent networks is based on the principles of linearity. We'll then be looking at Thévenin's theorem and Norton's theorem. These are two theorems which tell you the conditions under which equivalent networks exist and what those equivalent networks would look like. Then, as well as doing a few examples, we'll look at some exceptions when equivalent networks don't exist, some simple cases where they do exist where you might not think they do, and an outline proof of Thévenin's theorem. We'll start with a revision of the ideas of linearity and superposition. A system is linear, as we've seen, if you can express its output as the sum of all of the inputs multiplied by constant values. And if we have a system that obeys this formula, then we can say that we can determine the output by considering each of the inputs in turn while setting all of the other ones to 0, and then adding up all of those contributions to the output, and that gives the output when all of the inputs are present at the same time. When applying this to a circuit, it's important to note that a zero voltage source means just a wire, and a zero current source means an open circuit, nothingness, void, no current flowing through it at all. So I'll just do a quick example of this to refresh everybody's mind. Here we have a circuit, and we're asked what the current is through the 1K resistor. Well, we could write down Ohm's law for the two resistors and define the voltage here as 6 volts above the voltage here, and the current through here as 3 milliamps, apply Kirchhoff's current law to this point here, and solve the resulting set of simultaneous equations. However, there's a quicker way by applying the principles of linearity and superposition. We can set the voltage source to 0, and that means replacing the voltage source with a wire, so that would effectively give us this circuit here. Now, this is a current divider, and the current through this 1K resistor would be going in that direction, and just applying the current divider formula, we would get this contribution to the current as 3 milliamps times 2K, the other resistor, divided by the total resistance, which is 3K. The K's cancel, the 3's cancel, we end up with 2 milliamps. And then we can set the voltage source to its value of 6 volts and set the current source to 0. And that would give us this circuit. I didn't really need to draw these wire spurs. There is no current flowing through a zero current source. The whole right-hand side of this circuit is effectively doing nothing. So we've got 6 volts across what is a total of 3K in resistance. So the current flowing is going to be 6 volts divided by 3K, which is 2 milliamps. But this time it's 2 milliamps in this direction. So, principle of superposition, we add up these two contributions to the total current, and our net resultant current through the 1K resistor would be 2 milliamps going from right to left, plus 2 milliamps going from left to right. When you're doing this kind of problem, it's really useful to define a direction, which is the positive direction for current. Let's say that the positive direction for current is this way. In that case, this current here, I2, is a positive 2 milliamps because it's going in my positive current direction. This current here is a negative 2 milliamps because it's going against my positive direction of current. So I1 is actually minus 2 milliamps. That gives me my total current of minus 2 milliamps plus 2 milliamps, or 0. Nothing. No current would flow through this 1K resistor at all. And as usual, we can check it on the simulator. Here's the circuit, and if I ask it what the current is through the 1K resistor, nothing. Good. And that's usually a simpler way of solving these circuits than trying to solve all the simultaneous equations for the different currents and voltages in the circuit. Now, on to what I mean by an equivalent network. We've seen before things like this. An equivalent resistance. You can take any network of resistors and replace them with a single resistor, and the rest of the circuit would not change at all. As far as anything connected to A and B is concerned, this network of resistors behaves exactly like a single resistor, and the value of that resistor is the equivalent resistance of this network. And we can always do that for networks of resistors. However, what about this? Supposing that between A and B we don't just have resistors, but we have resistors, current sources, and voltage sources. Now what? Can we produce an equivalent to this, so that anything connected between A and B couldn't tell the difference between this network and a much simpler equivalent network here? In other words, can we find a much simpler network, for example, just a voltage source and a resistor in series, which will always give you the same voltage and the same current when anything is connected to the terminals A and B? And the answer is that in a lot of circumstances, yes, you can. You can find very simple circuits that look just like this, that behave in exactly the same way as much more complicated circuits here, so that the current flowing out of the terminals and the voltage across the terminals is identical for both of these networks, no matter what is connected to them. And that can make analysis of circuits much simpler again. The problem of equivalent networks is how to find these much simpler networks. That's the end of the first talk. In part 2, we'll be looking at Thévenin's theorem, which explains how to do this for a certain type of two-terminal network.